Our last unit was called kinematics. We defined kinematics on the first day of Physics 20 as the study of motion without regard to what caused that motion. In other words, we weren't going to pay any attention to forces in the last unit. This unit is called dynamics. It is also the study of motion, but this time we are going to pay attention to what causes the motion. In other words, we are going to pay attention to the forces. Dynamics is the study of motion with regard to what causes the motion. In other words, it is the study of forces. Now, that doesn't mean that the stuff that you learned in the last unit is gone until the final exam. We're still going to use those group B equations. Forces cause acceleration. And because forces cause acceleration, we're going to need to be able to use acceleration equations. But the focus in this unit is not going to be on that acceleration. The focus is going to be on what causes that acceleration. In other words, the forces. Does that make sense? Let's define a couple of terms that we need to be able to distinguish between going forward for this unit and for further units as well. Let's first define mass. Mass is the amount of matter that something possesses. In other words, it's the amount of atoms that something has. The mass doesn't change anywhere in the universe. Unlike weight, we'll talk about weight later on in this unit. Unlike weight, which does change depending upon where you are on Earth, depending upon where you are in the universe, mass doesn't change. If I have a certain number of atoms, then I have a certain number of atoms. It's going to be the same on Earth as it is on the moon. It's going to be the same in Vancouver as it is on the top of Mount Everest. Whereas weight, listen, quickest way to lose weight, might not be the easiest way, but it's the quickest way to lose weight. Go to the moon. Okay, a couple weeks later, okay, you weighed 120 pounds. A couple weeks later, you only weigh 20 pounds. You just lost 100 pounds from 120 pounds going to the moon. The only problem with that is when you come back to one of those yo-yo diets, go to the moon, lose 100 pounds. What happens when you come back? Just gain it right back. Gain it right back again. Your weight changes depending upon where you are in the universe. Your mass doesn't change wherever you are in the universe. It's the amount of matter that something has, the amount of atoms that something has. All right, mass is given by the symbol m, and the units for mass that we typically use. Anybody want to take a stab at that? Typical units that we're going to use for mass are? You take chemistry, don't you? Yeah, if you take chemistry, you're probably thinking grams, but in physics, we typically use kilograms. In chemistry, you use grams because you're typically, if I can say that, typically dealing with a smaller scale. Things are much smaller scale than in physics, where you're going to use kilograms, which are usually on a larger scale. So mass is going to be, for us in physics, measured in kilograms. Now, is mass going to be a vector or a scalar? Yeah, it's going to be a scalar. There's no direction associated with mass, right? I have a mass of 70 kilograms. I have a mass of 70 kilograms here, mass of 70 kilograms on the moon. But we're not going to say it's 70 kilograms to the right, or 70 kilograms down, or 70 kilograms to the south. 70 kilograms is just 70 kilograms. Mass is a scalar. Now, the next term is volume. We are not going to do a whole lot with volume in Physics 20 or in Physics 30. The only reason I'm defining it for you right now is so that you can distinguish between mass and volume. Sometimes people get these two definitions mixed up. We understand the difference between what mass is and volume is, but we get the definitions mixed up. The amount of matter that something has, or the amount of matter that something possesses, versus the amount of space that something takes up. Volume, the symbol for that is typically a capital V, and the units for volume would be, anybody want to take a stab at that one? Yep. Liters. Sometimes you see it as, yep, meters cubed as well. Now again, I wouldn't lose too much sleep over the units for volume. That's more of a chemistry thing. We don't deal with volume too much in Physics 20 or Physics 30. Mass, yes. Volume, not so much. Again, I just want to distinguish between the two. Now, is volume going to be a vector or a scalar? Is there a direction? Like, picture it this way. Would it make sense to say, oh, that pop bottle has a capacity of 2 liters to the south? It wouldn't make any sense, would it? So clearly, Volume is going to be a scalar. The other way to know that it's going to be a scalar is that when you look at the symbol there, volume, capital V, it does not have the little half arrow over top of it, so it must be a scalar. Has a half arrow, it's a vector. If it doesn't, it's going to be a scalar. Next one, this is when we're getting into the meat of the unit here, starting to get into the meat of the unit. The next one we're going to define is force. Force, and that's why I've capitalized that, because that's the most important one so far. Force is defined as, think back to Science 6. You first started talking about forces in Science 6. Remember your flight unit? The thrust force, the lift force, okay, the drag force. What was a force? Force was defined as it's defined as a push or a pull. Now, the good news here is, that's a pretty simple definition, right? The even better news, it doesn't get harder. The definition for force, whether you're in Physics 20 or Science 6 or your 4th year university, the definition for force is a push or a pull. We're not dumbing it down into a simple 5-word definition just because you guys are capable of understanding more, because you guys aren't smart enough. That's the definition. Okay, we're not dumbing down anything for you guys. Force is defined as a push or pull. The symbol for force is F with a little half arrow over top of it. The units for force, I'm not sure when the last time you saw force was. I know you saw it in Science 6. You've probably seen it since then at some point. No? Good guess. Joules is the unit. Joules is the unit for energy, and we will deal with that later on in this unit, just not yet. Yep. Newtons, good. So it's going to be measured in newtons. Now, is force going to be a vector or a scalar? Yeah, it's going to be a vector. If you go back to the little test that we did earlier, add a south to it. Does it make sense? Could you have a force of 25 newtons to the south? Yeah, that makes more sense than saying 2 liters to the south, right? Yeah, force is a vector. The other way you determine that force is a vector is, you see that little arrow over top, right? You see that little arrow over top, you know it's going to be a vector quantity. Now, there's 3 things that a force can do, 3 effects that a force can have. 3 things that a force can change. A force can change, is your hand going up there? Yes, it can accelerate. In other words, it can change the velocity of something. It can cause something to speed up or slow down. It can change the velocity by causing it to speed up or slow down. One other term goes with acceleration as well. We think of acceleration as speeding up or slowing down, but acceleration can be speeding up, slowing down, or changing direction. Yes. So it can change velocity. It can also change direction. Now, there's one more thing that a force can do that we haven't listed so far, besides causing it to speed up, slow down, or change direction. Yep. It can stop it, but that's changing the velocity, right? When you sit on a chair, you apply a force on the chair, right? And sometimes, this always happens. Depending upon the chair, you may or may not notice it. Okay, it happens to a higher degree with some chairs than it does with other chairs. When you sit on a chair, you apply a force on it, but you're not causing that chair to speed up or to slow down or to change direction. What are you doing? Don't raise your hand up? No? You're putting stress on it. Yes. Yes, you are pushing down on it, but what are you changing? Yep. The volume, yeah, okay. No, you're not changing the weight of the mass of it. If you're changing the volume of it, the only way you can do that is by changing the shape of it. So we're going to say force can change the velocity, the direction, or the shape. In other words, forces can deform things. Now, is it possible to cause a change in velocity and a change in direction? Yes. Sometimes it's one or the other. Sometimes it's both. Is it possible to cause a change in velocity and a change in shape? Yes. It's possible to do one or the other, but it's also possible to cause a change in both. Okay, when a car crashes into another car, the velocity changes because of the force, as does the shape of the car change because of the force. Sometimes at a low speed collision, though, the shape of the car doesn't change. Sometimes it's just the velocity of the car that changes. Does that make sense? Got another term for you. Inertia, which takes us back to the good old days of junior high school when we watched Bill Nye, the science guy, right? Inertia is a property of matter. Okay, yes, it is a property of matter. We've known that since we started watching Bill Nye, the science guy. But what is it? Like, it's a property of matter, but what is it? What property of matter does it describe? Somebody this morning compared inertia to momentum. And that was a really good comparison. Momentum and inertia are very, very similar to one another. Momentum we learn about in physics 30. We learn that momentum is loosely defined as how hard it is to stop something. The more momentum something has, the harder it is to stop something. A train moving down the track very, very slowly has a lot of momentum. Why? Why is it hard to stop? Because it's heavy, because of its mass, right? It's very, very heavy. So momentum depends upon mass. But a kid on a bicycle moving really, really fast down a hill also has a lot of momentum. Not because he or she is heavy, but because they're going pretty fast. Good, because of the velocity. So momentum, how hard it is to stop something, depends upon the mass of something and the velocity of something. That's close to inertia. Inertia, however, isn't how hard it is to stop something, it's how hard it is to change the motion of something. Which momentum could be included with that, right? Because how hard it is to stop something. Inertia is a more general term. How hard it is to change the motion of something. The tendency of an object to keep doing what it's doing, to maintain its current state of motion. If an object is moving, it wants to stay moving. If an object is at rest, it wants to stay at rest. What property of an object gives it its inertia? What makes an object that's moving want to stay moving? What makes an object that's at rest want to stay at rest? With momentum, there was two things. With inertia, there's only one that causes inertia. What is it? Newton's first law comes into play here, but that's not what causes inertia. That's kind of an application of inertia. What would be harder to change the motion of? You've got a little smart car out in the parking lot right now. You've got a big F-350 out in the parking lot right now. If you wanted to get one moving, to change the motion from an object that's at rest, right? Smart car at rest, F-350 at rest, which would be more difficult to change the motion of? The F-350. Why? It does need more energy, but why does it need more energy? Because it's heavier. The mass, yes, the mass. The heavier something is, the more it wants to resist a change in motion. The truck wants to resist a change in motion more than the smart car does, right? Because it's heavier. If something's heavy, it's difficult to make it speed up. It's also difficult to make it slow down. It's also difficult to make something start if it's heavy. It's also difficult to get something to stop if it's heavy. Inertia, which is a tendency to keep doing what it's doing, depends only on mass. Now, an application of inertia, the tendency of an object to keep doing what it's doing, is the first of Newton's three laws. Newton's first law, also called the law of inertia. Newton's first law, also called the law of inertia, says two things. Number one, it says an object at rest will do what? An object at rest will stay at rest, right? If it's the law of inertia, it's the law of keep doing what you're doing. If an object is at rest, it wants to stay at rest until, clearly objects that are at rest don't stay at rest forever, right? An object at rest, though, will stay at rest until not just a force, but an unbalanced force. Okay? This desk right now is at rest, right? I apply a force to it. Guess what? It doesn't move because it's not unbalanced. I have to apply an unbalanced force to cause it to move. So we're going to say an object at rest will remain at rest until acted upon by an unbalanced force. Parker, you see that I have unbalanced underlined? I have unbalanced underlined because that is probably the single most common omission from Newton's first law, is to say it will remain at rest until acted upon by a force. That's not quite correct, right? Acted upon by an unbalanced force. If I push on something with 10 newtons and you push on something in the opposite direction with 10 newtons, it's not going to go anywhere, right? The force is balanced. But if I push with 10 and you push with 8 in the opposite direction, it will go somewhere because now it's an unbalanced force. Does that make sense? Now, the second part of Newton's first law, the second part of it says an object in motion will continue in motion. It's going to continue in motion. It's not going to speed up or slow down. It's not going to change direction. In other words, it's going to continue in motion in a straight line at a constant speed until acted upon by an unbalanced force. So it's not going to speed up. It's not going to slow down. It's not going to change direction until acted upon by an unbalanced force. That doesn't mean a force, remember. You got a car traveling down the highway at 100 kilometers per hour. If it's going at a constant velocity, that doesn't mean no forces are acting on it. It means the forces that are acting on it are balanced. There's wind resistance on it. Yeah, there's also a force pushing it forward. They balance each other out, and that's why you're going at a constant speed in a straight line. One more term here. If the forces are balanced, if an object is going in a straight line at a constant speed, or if the object at rest, if the object's motion isn't changing, then that means forces are balanced. And if the forces are balanced, we say it's in a state of equilibrium. This doesn't mean it's not moving. This means it's at rest or it's moving at a constant velocity. If it's not in equilibrium, then what's going to happen? If the forces are not balanced, then it's going to either speed up, it's going to slow down, or it's going to, what's the third one? Change direction. If it's in equilibrium, it's either at rest and it stays there, or it's moving at a constant velocity in a straight line. If it's not in equilibrium, it's either going to speed up, slow down, or it's going to change direction.